Good morning, friends. So today again we have gathered here just to complete the first chapter, that is the structures of material. In the previous lecture we have seen about the defects in the crystals. So last lecture we have covered the defects, about the point defects. So we have seen the different kind of that point defects in that particular lecture. So the remaining defects we will cover in this particular lecture. So in the point defect we have seen some sort of that impurity defect, then stoichiometric defect, the four types of the stoichiometric defect that we have covered, and the non-stoichiometric defect. So there are two non-stoichiometric defects were there. So in this particular lecture we will just try to cover the remaining defects. So the first defect is the line defect. And what is the line defect? You just try to understand this term. So when the deviation from the perfect arrangement is present in the entire row of lattice points, then the defect is known as line defect. So the perfect arrangement is present in the entire row of lattice point. It should be an ideal condition, but if there is some deviation in that perfect arrangement of those lattice points, whatever may be the defect is occurred, it is called as a line defect. So there are the two types of the line defects are there. Those two types are, one is the edge dislocation and second one is the screw dislocation. So first, edge dislocation. What is the meaning of edge dislocation that we will see? So the one of the most common crystal structure defect is known as an edge dislocation. So this is very common crystal structure defect. So this occurs when there are some sort of that extra atoms inserted into the plane in the crystal lattice. So whatever the atoms are there, when some sort of that extra atoms are inserted into a plane in the crystal lattice, then the edge dislocation defect that may be occurred into the structure. So edge dislocation make it easier for atoms to slip past one another, making it easier for the metal to deform. So that metal deformation may occur because of that edge dislocations. So from this particular figure, you can be able to understand how those dislocations may be occurred over here. So these are the atoms arranged in the row structure, and here this slip plane, here you can be able to see. So in this particular section, the edge dislocation is occurred on that particular plane. So the atoms below this particular plane, they are having the different kind of that arrangement, and the atoms above this particular plane, this is having the different kind of that arrangement. So similarly for this particular figure, so when that shear stress is present on that particular structure, so these kind of that dislocation maybe gets occurred. So here we can be able to see whatever may be the unit step of slip, how it occurs. So this is the edge dislocation. Now this particular edge dislocations, one of the scientists, that is Jan Berger, he have designed some sort of that vectors to identify how the structure of that particular dislocation is occurred. So in the material science, the Berger vector is a vector often denoted by the letter B that represents the magnitude and direction of the lattice distortion resulting from a dislocation in a crystal lattice. So basically the Berger vector, whatever may be the magnitude and direction, so two things are there for the dislocation. First, we have to identify in what direction that particular dislocation is occurred, and second, we should know about in the quantitative figure how much is the distortion, that is 1 mm, 2 mm, 3 mm, likewise. So that is that 1, 2, 3, these figures are known as a magnitude. So the Berger vector gives us a magnitude as well as the direction of that particular distortion. So the vector magnitude and direction is best understood when the dislocation bearing crystal structure is first visualized without a dislocation. So that is the perfect crystal. So we should first know the perfect crystal. So we have to understood about the perfect crystal, and after that we can be able to know the magnitude and direction of the dislocation. So in this perfect crystal structure, a rectangle whose length and width are integer multiplications of A, the unit cell edge length, that is, and is drawn encompassing the sides of the original dislocational origins. So once this encompassing rectangle is drawn, the dislocation can be introduced. So this dislocation will have the effect of deforming not only the perfect crystal structure but the rectangle as well. So here we have to draw the rectangle. Here we can be able to see that is the burger vector. So suppose if this crystal is normal, we have to draw the rectangle. After the deformation, there is same sort of the deformation in that particular rectangle also along with the crystal structure. So this gives us a magnitude as well as the direction of the dislocation. So this is the very important vector as far as that edge dislocation and screw dislocation is concerned. So this is one realistic example of the edge dislocation. Now we are knowing about the sweet corn. So in that sweet corn, so that corns are structured in the well manner, but somewhere some sort of that corns that has been deviated from its length. So this kind of that deviations somewhere. So here in this upper portion you can be able to see there is some sort of that different arrangement. It is arranged in the line, but in this particular location some sort of that line has been gets disturbed and this line has been changing its direction. So this is called as an edge dislocation. So this structure gives you an idea about this. So suppose these are the atoms here that green color indicates, but because of the distortion, so those atoms are disappeared in this particular structure. So that's why this is the called as an edge dislocation. So here if you count whatever maybe the edges are there, so that are having the different kind of that count, but at the bottom the different structure is observed. So the second, that is the screw dislocation. So a dislocation, the definition of the screw dislocation is that is a dislocation in the lattice structure of the crystal in which the atoms are arranged in a helical pattern that is normal to the direction of the stress. So that when the helical arrangement or that helical pattern, when it gets dislocated, so whatever may be the defect in that lattice structure is occurred is called as a screw dislocation. So basically all the atoms are arranged in the helical pattern and that helical pattern will be gets disturbed, that is that lattice structure will be gets disturbed or dislocated, and because of this whatever may be the defect occurs is called as a screw dislocation. So this figure will be gives you an idea about the screw dislocation. So here we can be able to see that how that screw dislocation will be gets occurred. So suppose this is the normal rectangle initially, but when some sort of that forces has been occurred, so this is the particular location which shows you and some sort of that force. So when some sort of that forces has been gets occurred, this particular edge will be gets or this particular surface will be gets slipped, and so this particular dislocation is called as a screw dislocation. So here we can be able to again draw some sort of a burger vector just to identify about the magnitude and direction of the screw dislocation, and this particular structure of the atoms will give you an idea about this how that dislocation will be gets occurred. So here this is the helical structure, so that has been gets disturbed because of the forces and which creates the screw dislocation. So this is the one more diagram which gives you a comparison about the edge dislocation and about the screw dislocation. So here you can be able to see the edge dislocation. So here in this particular pattern, in that edge dislocation, whole surface will be gets dislocated, but in this particular screw dislocation, only this much portion will be gets dislocated. Okay, so here you just try to remember this thing. In the edge dislocation, whole surface will be gets dislocated from its original points, but in the screw dislocation, only this particular some surface will be gets dislocated. So here this is the diagram. Not only whole structure will be get disturbed, only up to this portion the edges has been gets disturbed. So this is the screw dislocation. Now after the line defects, there are only two types of the line defects that we have seen, that is edge dislocation and screw dislocation. Now next is the surface or planar defects. So what is the surface or planar defects? So surface imperfection arises from a change in the stacking of the atomic planes on a across boundary. So surface imperfection, that is the change in the stacking of atomic planes. Stacking in the sense when we are arranging the material, okay, on any way. So whatever the atom stackings it is there, so that atom stacking it will be gets disturbed and some sort of that planar or surface defects maybe gets occurred. So the change may be one of the orientation or of the stacking sequence of the atomic planes. So basically, just to understand this particular thing, I will give you one example. So in the composite material, basically that material has been manufactured, or we can say that is basically that has been designed according to some sort of that fiber directions. So those fibers basically has been mixed with the resins, and that has been stacked on some sort of that particular any surface. So when that stacking is going on, might be there are the chances that stacking sequence maybe gets disturbed, that fiber maybe get disturbed, and so there are the chances that surface or planar defects maybe gets arranged. But in case of metals, whatever the atoms are there, that has been get disturbed, that stacking sequence has been get disturbed, and the surface or planar defects may be occurred. So in the geometrical concept, the surface imperfection are the two-dimensional. They are of two types, that is the external and internal surface imperfections. So these are the two types of the surface defects. First is the external defect and second is the internal defects. So internal defects means the internal surface imperfections are the imperfection in the sense defect. So the internal surface defects are the defects which occurred inside the crystal. So which is occurring basically inside the crystals. So that's why it is called as an internal defect. So it is caused by the defects such as a grain boundary, twins boundary, or stacking faults. So these are the three types, that is the grain boundary defect, that is the internal defect. In the internal defect, that is the grain boundary defect, twin boundary defect, and stacking fault. So what is the external surface defect? That is the exterior dimensions of the material represent the surface at which the lattice abruptly ends. That is, each atoms at the surface no longer has the proper coordination number and the atomic bonding is disturbed. So the exterior surface may also be very rough, may contain tiny notches, and may be much more reactive than the bulk of the material. So basically some sort of the notches, some sort of that surface roughness that will be gets occurred and which we can be able to visualize, that is on the external part of that particular material. So that is called as an external surface defect. So next is in the internal defect, the first defect is the grain boundary defect. So there are the imperfection which separate the crystals or grains of different orientation in a polycrystalline solid during the nucleation or crystallization. So here we can be able to observe, so that these are the grain boundaries are there, and every boundary or inside the every boundary, so some sort of that different kind of that arrangement of the grains we can be able to see, and this is called as a grain boundary defect. So it is a two-dimensional imperfection during the crystallization. So it may be occurred during the crystallization, and new crystal form in a different part, and they are randomly oriented with the respect to the one another. So here that arrangement is the random orientation with respect to one another, but this is the grain boundary, and inside that every structure is having their own identity. So this is the grain boundary defect. So twins boundary, if the atomic arrangement on one side of the boundary is mirror reflection of the arrangement on the another side, then it is called as a twin boundary. So twin boundary here you can be able to see. So just focus on this particular location. So here exactly the mirror image you can be able to identify. So this mirror image has been divided by this particular line. So these are the twins boundary. So this is the twins boundary defect. So an atomic arrangement gets disturbed. On one side of the boundary it is the different one, and on the second side that perfect reflection or mirror reflection will be gets occurred, and this is the twin boundary. As they occur in a pair, they are called as a twin boundary because this is occurred in a pair. So exactly the two boundaries which is having the identicals. So that's why it is called as a twin boundary defect. Now the stacking fault. This is the last defect as far as that surface or planar defects are concerned. So whenever the stacking of atomic planes is not in a proper sequence throughout the crystal, the fault caused is known as a stacking fault. So when the stackings of atomic planes is not in a proper sequence, means what? So suppose if there is some sort of that arrangement of the stacking sequence in any crystal, suppose in the abscisic crystal it is there, and if the whatever may be the ideal condition or that ideal stacking sequence what we expect, if it is ABC, 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 but unfortunately some sort of a defect maybe gets occurred and that stacking fault may changes the sequence like ABC, ABA, BAB, likewise the region in which the stacking fault occurs ABAB, that forms the thin region and it becomes the HCP, and because of this that abscisic crystal will be converted into the HCP. So this thin region is surface imperfection and it is called as a stacking fault. So this particular figure you can be able to identify how that stacking fault will be occurred. So this is suppose the perfect crystal is there. So that in the perfect crystal that CBA, CBA, CBA. So these kind of that suppose atomic arrangement if it is required or if it is called in a perfect crystal. But in the realistic condition, if the stacking fault is there, that particular structure will be likewise ACB, ABA. So this will be expected that ACB, but it is changed as an ABA. So once again that BC will be gets introduced and this structure will be not having any proper sequence. So this is the called as a stacking fault. So these are the all the defects that we have seen. So in the last lecture we have covered about the point defect. In this particular lecture we have covered about the line defect, that is the edge dislocation, screw dislocation, then the surface planar defects, that is the external planar defect and internal planar defect. So in the internal planar defect, that grain boundary defect, stacking fault and twin boundary defect. So these many defects that we have covered. So I hope you have enjoyed this particular lecture, and in the next part we will just go with the remaining concepts. That is, we have seen up till now some sort of that deformation which is basically related to the elastic deformation. In the next lecture we will just go with the plastic deformation. So what is the meaning of plastic deformation and all those things that we will cover in the next lecture. So thank you very much for the patience listening.